Okay, so now we've got to cover hypothesis tests for quantitative variables. Okay, so with a hypothesis test, all right, let's settle down here. All right, so let's say I don't know. Let's say you bought you become obsessed with apples now, okay? And you want to and let's say this guy says, "Hey, I got this great deal on apples, okay? I'll sell you a truckload of 10,000 apples, okay?" And you're like, "Oh, okay, that's a good deal, but I know, I want to make sure these apples are the proper size, okay? And because if you sell me apples that are too small, that's a bad deal, right? I don't like small apples. I want to make sure I got these nice, good sized apples here, okay? So in your mind, so the guy says, "Sure, I promise you that the average apple size is 250 grams, okay? So you buy a truckload of apples. Okay, and the seller says the average size in the truckload is 250 grams. Each apple, 250 grams. So those are actually pretty big apples. So I don't know. And yeah.
The average size of the truckload is the population.
Yeah, so the population, the truckload is the population, okay? And the seller says the average size is 250 grams, okay? And you say, okay, I've had some bad deals on Craigslist, so I don't want to get burned here, okay? So I want to make sure that you're not just tricking me, okay? So you say, okay, I'm going to go take a random sample of apples, and I want to make sure that truly the average size is 250, and I don't want it to be less. Okay, so you take a random sample.
So half an apple.
Yeah, so maybe that's too big, but whatever. Okay, yeah, it says these are jumbo apples. Okay, random sample of apples. Okay, and let's say you took you took a sample of 10 apples. And the average size of these 10 apples, so what symbol do I use for my sample average? X bar, not p hat. P hat is only for proportions, and proportions are only for categorical data, okay? So let's say the average size when I took the 10 apples was 235 grams, okay? And the standard deviation was 9 grams.
Of the sample.
Of the sample. Okay? Standard deviation in the sample is 9 grams. So is this evidence that the apples in the truck actually have an average that's less than 250 grams? That's what we're asking. We want to do a hypothesis test. So
the mean gives you 235, which is way less than 250.
yeah, my sample average is 235, which is less than 250. Okay? So you're like, what are you trying to do here? Okay, you're trying to sell me some small apples here? I just took a sample of 10 apples and and I got 235 grams, okay? What are you trying to do? And then the seller says, hey, hang on a second, don't be accusing me of anything, alright? The average is 250 grams. So when you just took your random sample of 10 apples, you just got unlucky and you just happened to pick 10 small apples, okay?
Okay.
That's what he's saying. So do you believe him? Or do you say, no, I got 235 grams here, and that's too small?
Well, it's
I
about
wanna
6
refund.
grams above the
Okay,
one
so they say,
standard
alright, I
deviation.
got Mr. Chen here on speed dial, he can answer these types of questions. Okay? So they call me up and I say, oh, hello? Oh, apples again, alright. Alright, so I'll say, okay, let's do a hypothesis test, okay? So here, we want to test, is the average weight 250 grams or not, okay? So what do I write here for my null hypothesis?
Equals 250.
Okay, so how can I write the average weight is 250 symbolically?
Equals
No, not
X
A.
bar.
Not
X
X bar.
Sorry.
T.
Okay,
X
X
bar
bar is
E.
better, but it's not X bar.
The T.
It's the mean of the population, which is mu. Mu equals 250. We want to know, is the mean of the population 250? Or we would be really upset if the mean is what? Less than 250. If the mean was over 250, we'd be happy, okay? Or Appleman would be happy. Appleman. I'm gonna save the day. And keep the doctor away. Alright. What? Vitamin C and pectin. So these are our null and our alternative hypothesis. And what is our data? Our data is X bar is equal to 235. My sample size, my standard deviation is 9, and my sample size is 10. So if we want to calculate the p-value, right? The p-value says if the null hypothesis were true, what is the probability that I take a sample of 10 apples and get an average of 235? That's what we want to know. If the null hypothesis were true, what's the probability that I take a random sample of 10 apples and get an average of 235? If that probability is pretty high, then maybe I got to give benefit of the doubt to the salesman. If the probability is low, I'm going to say I don't want to buy these apples. All right, so we're going to ask, what is the probability of taking a random sample of 10 apples and getting a sample average of 235 grams if the population average is really 250 grams. Yes?
How can we tell the difference between what we're supposed to do in this problem and the other problems? Because they all kind of sound the same. What is the probability of getting this if we have this n and this x, or you know what I mean?
So, I know they sound kind of similar,
Numeric versus categorical, maybe? Or no?
but I don't know. In my mind, they're all very distinct. But I don't know.
Any keywords
Give us
to
some
look for?
keywords.
Yeah.
Well, all the other ones.
Okay, so if you're getting standard deviation and if it talks about mean and average, you know you're dealing with a numeric variable because you can't have a mean and average of a categorical variable. And if you ever see the word proportion, you know you're dealing with a categorical variable because you can't take proportions of numeric.
So mean, average, and standard deviation.
Will tell you you're dealing with numeric. Proportions, categorical. Well, then you just think, right? The weight of an apple, that's going to be numeric. So if we come this far and you can't tell the difference
But
between
if you say heavy or light,
that's
but you're not actually talking about weight, you're talking more like.
okay. So like you go,
Like
you go in the this person's in the heavy category and this person's in the
Yeah.
light category. Okay, so I mean then we're dealing with categories. Okay, so I mean.
Kinda like age could be, but if you put like teenagers and adults. Or
Right,
something
right.
like
So
that.
I mean, you got to read the problem, okay? And we can always think of scenarios that are like set up to be traps here, okay? I don't think I don't write my problems to be traps, but people make mistakes and then they're like, you're being tricky.
The best way,
I promise I wasn't.
the way that made me really understand it is you said it's numeric if you can compare this to this. Like if you can numerically compare it. Like this
Yeah.
is more than this or this is less than this. Like you
Right.
can't say I'm more male or, well, damn it.
Yeah.
Alright,
Yeah, and
something
I mean,
else.
you can always compare things and
Yeah.
stuff, but yeah, it doesn't make sense to say there's a difference in the
Yeah.
quantity of maleness, right? I have 30 more man points than you. So.
Yeah.
Is that a lot or a little? Okay. So anyway, this is what we're asking here, okay? So if the null hypothesis were true, what would the mean of my sampling distribution be? 250, okay? If the true average weight of apples in this truckload was 250, every time I take a random sample, I should be getting 250, okay? So I'm going to draw something that looks like the normal distribution with 250 in the middle. And what did I actually observe? 235. And I want to know what's the probability of getting 235 or less. So I would get, you'd think I'd get a z-score, but I'm not using the z-distribution. I'm using the t-distribution. So I'm going to get a t-score. Okay, t-score, or this is my test statistic. And it would be just like the z-score, but the test statistic, or t-score, so I would do what? No. On the top, I do 235 minus 250, and I divide by my standard error. What is my standard error? Hence, it's the same as my standard error for a confidence interval. S over square root of n. So this would be 9 divided by the square root of 10. So I get like 3 point something, or I don't know. A little less than 3. 2.846. Okay, so 2.85. So I do 2.846. So I do 235 minus 250 divided by 2.846, and I get negative 5.27. So I'm on the phone. I'm like, oh, okay. Oh, the average was 235, and what did he claim? He's claiming 250, and you took 10 apples, and you got an average of 235, and the standard deviation was 9. Okay, well that puts you at 5.27 standard errors away from the mean. Does that seem like a lot or a little? A lot, okay? Now, we can, standard errors, I mean, it's a little bit different because it's a t-distribution, okay? But 5.27, that seems like a lot, and it is.
So the
okay?
t-score and the test statistic are the standard error?
It's the number of standard errors you are from the mean.
Oh,
okay?
that's right.
So the z-score is the number of standard deviations you are from the mean, and the test statistic is very similar except you're doing standard errors. So we are 5.27 standard errors from the mean. So that seems like a lot. Okay, and I'm going to say that seems like a lot. Alright, so this is where the t-distribution differs drastically from the normal distribution. Okay, so turn to your t-table in the book with me, page A7.
So it would have to be closer to 0, right? If it doesn't, for it not to look so
Right,
apart. Okay.
right. So like you said, 235, that's way less than 250, and you're absolutely right, okay? That's 5.27 standard errors from the mean. So go to page A7. How many degrees of freedom do I have? 9. 10, n minus 1. So 10 minus 1 gives me 9 degrees of freedom. Okay.
You wanna be 95%.
So if I look at the row 9 degrees of freedom, I have 1.383.
Sorry,
Hang on, let me just write this down. So I'm just copying this row of numbers. Making a confidence interval, so there's no confidence level. Okay. All right. So this is what we have in the table. Is that good with everyone? Okay. So what this means is that if the number I got here, okay, whatever you get here, you can just ignore the negative sign, negative or positive, because it's symmetric. Just ignore the negative sign if you get one. Okay. This says if I got the number 2.821. And I had 9 degrees of freedom. So if this number was 2.821, the amount in my tail, so if I was at 2.821, the amount in my tail would be 0.010. That's what this says. Does that make sense?
Say that one more.
So, so what this table says is that if this number happened to be 2.821, the amount in my tail would be 0.010 by looking at this thing, the subscript on the t.
To the left?
Well, if it was negative 2.821, then it's the amount in the tail. So whatever is in the little triangle wedge piece is going to be 0.010.
So
okay.
there are no two.
Yeah, well, because it's symmetric. So whatever you get a negative or positive. Just you don't look up the same equivalent number over here. So if the number happened to be 3.250, how much is in the tail? So if you get 3.250, what happens? How much is in the tail? 0.005. Okay.
So it's the area in the tail?
Yeah, it's the area in the tail. Okay. What if my number was not 2.821 and not 3.25, but what if it was exactly 3?
Sorry?
So okay, so if t was 2.821, we've agreed that the amount in the tail is 0.010. Okay. If t was 3.250, we've agreed that the amount in the tail is 0.005.
So that's right through the middle?
What if the amount was at 3?
Subtract each other.
Just
No, I
to
wouldn't.
just find the middle of the t's.
Okay. Not even. I wouldn't even have to
At the
bother
middle.
that. Okay. Just make it simple for ourselves. Just say if the number was 3, 3 is in between this number and this number. So I don't know how much is in the tail, but I do know it's between 0.005 and 0.010. Okay, does that make sense? Okay, so my T is 5.27. So how much is in my tail?
We know it's
Less
above
than-
0.001.
Wait, 0, 0.
Less than 0.001, okay? Cause
Is
so
this
my,
table called, is this a table called anything?
it's called the T table. Alright, it's very original, yeah. Us statisticians,
Tea time.
we didn't excel in creative naming awards, okay? So where I am is at 5.27, okay? If I happened to be at 4.297, I know that the amount in my tail would be 0.001, okay? But where I'm actually at is 5.27. So I don't know exactly how much is in there, but I do know for certain that the amount here is going to be less than 0.001. So my p-value is less than 0.001. Is that all right?
You would never say equal to or less than.
You would only say equal to if you got one of these numbers exactly. Okay? If you got anything else, you would just say less than or greater than or something like that. So I don't know exactly what it is, but I do know for sure it's less than 0.001. Yes, sir.
Why is it less than if 0.001 is 4.297? Because 5 is higher than 4.
Mm-hmm. What do we notice? So as we go out in this direction on this row, the numbers get bigger. What about the numbers on the top? They get smaller, okay?
So whether it's like 10 or 20, whatever that number is, it's
Yeah.
going to be less than
0.001, yeah. So if my T was 20, I still don't know what it is, but I do know for sure it's less than 0.001. Okay, and that's the most precise we can get at this point.
Oh, so in the
with
book
table.
there's only
Yeah,
that
there's
number.
only these many columns. Okay.
Oh, okay. So any number above that.
Yeah, whatever. You're just gonna say less than 0.001. Okay, that's it. And if you had a computer, it'll give you a more specific value.
That's a 001.
0.001. Okay. So then, so my p-value is less than 0.001. What is the meaning of this p-value?
Or T value.
That's p. P-value.
0.001?
Yeah, 0.001 is my p-value. That's the answer to the question. What is the probability of taking a random sample of 10 apples and getting an average of 235 grams if the truck average was really 250 grams?
Very rare.
Okay, very rare, less than 1 in 1,000. Okay, so the guy selling the apples is gonna say, no, you just got unlucky. You just happened to pick a random batch of small apples, but I promise the rest are much bigger. Okay, I promise the rest have an average of 250 grams. And you say, no, I got the statistician on the phone, and he says the probability of me selecting 10 apples at random and getting an average of 235, that's less than 1 in 1,000. So I think you're selling me small apples here, okay? Deal's off, okay? And then he goes, and there's and that's what we conclude here, okay? Yes.
So we would need to explain what that is on quiz.
Yeah. So I mean.
Yeah, how do you?
So we would say the p-value, okay, so if alpha was 5%, okay, the p-value is less than alpha. So we reject the null hypothesis, okay? We conclude that the average in the population is less than 250 grams.
What was alpha again? Sorry.
Just assume 5%.
Oh, that's okay.
And p-value is 0.010.
0.001.
Oh,
0.001.
Oh.
P-value is less than.
0.001. Yeah. Don't put this 2.82 stuff in your notes. It'll confuse you. All right. Is that okay?
We take that even though we know it'd be less than 0.001.
Yes. We just say, all right. I don't know what my well, I mean, I don't know exactly what the p-value is, but I do know it's less than 0.001. And if it's less than 0.001, it's certainly less than 0.05, right? So, don't erase this.
Wasn't that important?
Okay, we still got more to cover here. We can do it. We can do it. It's easy peasy. All right. Is this so far okay?
So you take that number, the 5.27, and you look on the
Yeah, you look on the table and you say, okay, where does 5.27 fit in this row?
It's
Once you
less
figure,
than-
and then so 5.27 is bigger than that, so we say it's less than 0.001. If this number happened to be what? 1.9, what would I say my p-value is?
Between 1.8. Sorry.
0.50.
Yeah, so if my number ended up being 1.9, the answer would be between 0.050 and 0.025. That's how it works. All right.
And you will give us a T table or we'll use one?
Yeah, I'll give you the T table, okay? Nobody has to memorize a T table. Even I haven't done that.
Sure.
I go home memorizing the T table. One day. All right. Okay, so we've got a little bit more, but I'm gonna just present the stuff to you, and maybe it won't sink in this first time around. That's okay. We're gonna see some more of it next week, and then the week after, and then and I hope it'll sink in, and then comes the final. Okay, so the first time around everything always sucks. So. Here we go. So that was when we're dealing with one sample, okay? And then we had confidence intervals for one sample and proportion tests for one sample, and then we had proportion tests for two samples, and now we're going to have confidence intervals and proportion tests for two samples, but now with numeric variables, okay? I know. Okay, so we got hypothesis tests and confidence intervals, okay, for two samples, and we're dealing with means or numeric variables, okay? The overall concept of all of these things is still exactly the same. The only thing that changes here is how we calculate the standard error. Having all sorts of noises. I'm always afraid that
Fire alarm?
not a fire alarm, just something embarrassing would show up on, I don't know, someone's phone or something. Okay, so the only thing, overall concept changes. The biggest thing, the overall concept exactly the same. The only thing that changes is how we calculate the standard error and all of this stuff, okay? So for both of these things, the standard error is just going to be an ugly formula that we can't do anything about, all right? S1 squared over N1 plus S2 squared over N2. What is S1 going to be? Standard deviation of
Part 1.
the first sample. N1 is sample size of the first sample. S2, standard deviation of the second sample. N2, size of the second sample, okay?
Other two is square.
Yeah, the other two, up top is the square, okay? So you square this, divide by N2. That's going to be the standard error. And then the degrees of freedom is going to be n minus 1, but use the n of the group with fewer items. So if I took a sample of 10 men and a sample of 12 women, how many degrees of freedom do I have? 9, okay? Because I've got 10 men, 12 women, it's going to be n minus 1, and I just have to decide, do I use the women or the men? Take the group with fewer items or fewer people, so the men. So 10 minus 1 is 9. That's how we get degrees of freedom. Okay? Alright, so for a confidence interval, concept exactly the same. We are creating a confidence interval for the true difference in means. Okay? Confidence interval for mu1 minus mu2. Okay? So this is for the true difference between means. So we have here x1 bar minus x2 bar plus or minus t star times standard error. And what is the standard error? This ugly thing. And how do we pick t star? Table. You use this degrees of freedom and your confidence level. So that's easy, right? And this is it. So it's no, that's it. The overall concept's not any different here, okay?
You have to memorize that.
And not even memorize it, you just put it on your note sheet, okay? The hardest part is reading the problem and saying, aha, here I have 2 samples and I'm dealing with a mean and I'm making a confidence interval. Once you figure that out, you got this right here, okay? But maybe you read it and if you read the problem and it's supposed to be means and you think you're doing proportions, you're going to be in big trouble, okay? And and it shouldn't happen, but it happens all the time, okay? I mean, we got to note that we're dealing with means and not proportions, okay? So if you come this far and you can't tell the difference between means and proportions, then you're in trouble.
On the practice final you gave us, it won't be clear, like we'll have to figure it out.
Yeah, I'm not going to be like, on the answer sheet. So I have an answer sheet for the practice final. On the answer sheet it says this situation is this, and this is what we do. But on the practice final I don't tell you, okay? Just like the final exam I don't tell you. Alright, so let's say,
Is the answer sheet the study guide?
no, there's a, I guess I didn't make a,
Is there study guide?
yeah, there's a study guide. Oh, maybe I don't have answers posted. I go over the answers in class, that's what's going on. Yeah. Okay, so for here, let's say we go through a problem, okay, and we're going to make a confidence interval for the true difference in heights, or difference in mean heights of men and women.
Does that say true difference?
Yeah, the true difference in mean heights of men and women. And so here's my data. I surveyed 30 men, and let's say 25 women. The mean height of the men, let's say, was 5'10", 70 inches, and a standard deviation of 3 inches. Let's say the mean height of the women was .54, so that's 64 inches with a standard deviation of, we'll say, 2.8 inches. So let's make a confidence interval.
That's all given on the test?
Yeah, you should be able, if I give you all of this information, you should be able to make a confidence interval.
Oh yeah, what's that word between a and difference?
The true difference in mean heights of men and women.
But you could, instead of giving us the actual N1 and N2, you could say, there are this many women, this many men, the mean is this, but you'd always give the standard deviation straight. You wouldn't make us figure it out, would you?
No, because I'm nice. I could, and that would be well within my quote rights, because that is something we've learned and covered. But you guys already took a midterm and a quiz on that, so I will just pretend like everybody still knows and remembers the standard deviation formula and how to do it, but I know I'm lying to myself. Okay, so let's do this, okay? Did anyone already figure this out?
Whenever you just plug it in and it just something.
How do you know what the degrees of freedom are when you have two ends?
Use the.
Sorry.
Oh, okay. Oh, let's do a 95% confidence interval. Okay, go ahead and
So
what?
that's it?
That's it. Yeah. So let's whether you got to this point or not, okay? You can go back, watch the video, pause it. These are the numbers that you should get. Okay. Are we not matching up? 0.7833. Okay. So when you do this, okay, and if you're having trouble with this, just you can check the calculator work and stuff. But, so I got 6 plus or minus 1.617. Okay. So I'm just rounding off to 1.6. So if I do 6 plus 1.6, that takes me to 7.6, and if I do 6 minus 1.6, I get 4.4. So this says, I would write, I am 95% confident that the average male is between 4.4 inches and 7.6 inches what? Taller than the average female. Okay? So based on this sample of 30 men and 25 women, I am 95% confident that the average male is between 4.4 inches and 7.6 inches taller than the average female.
I got as far as 7.833.
Okay.
So I forgot what you got to say.
Yeah, 7.7833, so I do the T star 2.064 times 0.7833, and that gives me 1.617, okay? The 6 comes from 70 minus 64.
Right.
Alright.
So you're always gonna give us all the information, all we have to do is plug in. basically.
Yeah, you gotta figure out what you're doing, and then you plug in, and then it's easy.
But you're getting T 2.064 from the table, right?
Yes, T 2.064 comes from the table, yes.
How do you ever say that if an average male is between 4.7 and 6.6?
Okay, so I'm just telling you this is what the conclusion is, so then if something changes up, you know how to model your conclusion, okay? What if,
Wait,
yeah,
one question. When do we use the degrees of freedom?
when you look up the table, to look up your T star in the table, you need the degrees of freedom,
Okay.
okay?
You're gonna give the degrees of freedom and the T star?
I will not give you
25
degrees
minus
of freedom,
one.
you can figure out degrees of freedom.
Oh, but the,
To figure out.
yeah,
25
because
minus
there's 25.
25 minus 1 is 24.
The fewer
And then
one.
35
And then now I will give you the percentage. So I'll give you these 6 numbers and what level confidence, okay? And you should be able to do everything else, and you need to be able to say this at the end, okay?
You'll give us what, 6 numbers? The DF?
These
Okay.
6 up here.
25 minus 1?
For the degrees of freedom? Yeah, it's n minus 1, okay? But use the n of this group with fewer people or items.
Oh, right.
So which group is that?
25.
25. Okay.
But
Yes.
it was your choice to use the 95%.
Yes, that was my choice.
Okay.
Okay, and I will specify that.
And then we have to know how to word it correctly.
Yes. Okay, and we'll talk about the wording because people get mixed up on the wording and stuff. All right. What if so do we have evidence based on this confidence interval? Do we have evidence that men are taller than women?
Yeah.
Yes. Okay. What if I did the same problem, but I looked at children, and I want to know, is there a difference between, let's say we went to elementary school, we went to 5th grade, and we measured boys and girls in 5th grade. And we said, is there a difference in the average height of boys and girls in 5th grade? And we did this, and let's say we did all the work, and our confidence interval was 1.1 inches plus or minus 1.9 inches. Okay? So then if I do the minus, I get negative 0.8 inches on the low end to basically 3.0 inches on the high end. And this was average height of boys minus average height of girls. Okay. Do I have evidence that 5th grade boys are taller than 5th grade girls? If you say no, tell me why not. Because the answer is no.
I mean, it's impossible to be negative 0.8 inches.
No, it's not that. Okay, so if I had to write the sentence here, I'd say I am 95% confident that the average boy, I guess average 5th grade boy, is between 0.8 inches what? Shorter. Okay, it's between 0.8 inches shorter and 3.0 inches taller
It's too much of a
than what? Than the height of the average 5th grade girl.
Because you can't be shorter and taller.
Right. So the reason is that we don't have evidence of a difference. We do not have evidence of difference, and the reason is because 0 is within our interval. 0 is within the interval. You guys remember that rule for the proportion difference? You guys remember that rule for the proportion difference? Same concept applies here. Zero is within the interval. Yes.
This might be a silly question, but I don't understand how you know that you're talking about guys being the male being taller rather than female.
It depends how you set up your confidence interval. It depends on that, okay? And so, you know, maybe this is a detail that we can get into in later classes, okay? But when I'm just introducing the topic,
So it's N1 is
is group 1 is whatever it's in reference to, okay?
Okay.
But so the last one I said I'm 95% confident that the average height of men is between 4.4 inches and 7.6 inches taller than the average height of a woman. I could equivalently, if I set up my confidence interval differently, it would be the absolute same thing for me to say I'm 95% confident that what? That the average height of a woman is between 4.4 inches and 7.6 inches shorter than the average man, okay? And that would be, that would correspond to negative numbers if I had switched the setup of my confidence interval. But they're telling you the exact same thing.
and one other thing, what if there's no shorter or taller? What if it's two things that one is not necessarily less or greater?
Okay, so all numeric variables,
Oh,
you can compare larger, smaller, greater, less, bigger, whatever, taller, shorter, okay? All numeric variables can be compared, the quantities can be compared. Okay, so we can say, you know, at the least we can say is that the height is between 8 inches less and 3 inches greater than, okay? And less and greater than work for all measurements, okay? Yes, John?
You always have to write that evidence of difference on top of that answer? Or we could just write that one?
No, but I might ask you a question like this on,
So what is 0 again?
so 0 is in between negative 0.8 and positive 3,
Okay.
okay? And
Is
because,
this separate section?
yeah, because 0 is within the interval. So we talked about this for proportion, right? Like creating confidence interval for 2 sample proportion, or proportion, a confidence interval for a difference in proportions. We said if 0 shows up in between the ends of the interval, then you don't have evidence of a difference. Whereas if 0 is not inside the interval, you do have evidence that there's a difference between the proportions. Okay? The same concept applies here, but now it's not proportions, it's now means. Yes?
So when you did the calculation, it was negative 0.8, but when you did the conclusion, it was just 0.8. You just get
Because
rid
it's
of
0.8
all the
inches shorter. The negative shows up in the word shorter.
Right.
Because shorter
I
means
get it.
less.
No, I know
Or
that it's
negative.
less because it falls in the.
So I mean, I could say.
So let's say when you do the conclusion, do you just.
No, you don't
write
get rid of the
negative,
negatives, okay? You don't get rid of the negatives. The negative shows up in the word shorter, okay? The English word shorter implies a negative quantity, okay? Like
In other words, if you took the word shorter, I'm gonna have to put the negative sign in.
Right. Yeah, so I could say, you know, the credit card applied a charge of negative $10, or the credit card, you know, subtracted $10 or whatever, you know, I mean, so our language will cover the negative signs, okay? It doesn't just disappear. Yes?
One more thing, if you gave us this problem and we figured all that out, as a conclusion, we wouldn't put I'm 95% confident, we would just put we do not have evidence of the difference, right?
You should get used to the 95% confidence type of writing also.
So we should write that, we would need to write both?
I don't know, I'm trying to think.
You know what I'm saying?
Yeah, I know what you're saying. I know what you're saying.
Like if it
and
doesn't
I
work
think
out,
the question
we
is,
know.
how big of a jerk are you going to be when it comes to grading, right? Like if we wrote one conclusion but not
No,
the other.
I don't even mean that. I basically mean like, do we still have to say
So,
like
okay,
between this and this if like you realize? that
Okay,
there's
so
a-
I will try to
word
be
is wrong,
specific,
but
right?
you
I'm not
know
gonna
what we-
I'm not gonna be like this
Oh.
and go explore in the playground, okay? I structure all of my questions so that you got to give me a very specific thing that I'm looking for, okay? So I will say, you know, please finish this sentence. I'm 95% confident that ... Then you got to write the correct thing, okay? Or I might say, do we have, based on this confidence interval, do we have evidence of a difference? And you have to write yes or no.
So evidence
okay?
of difference is always with 0.
For when you have a confidence interval for two samples, okay, whether it's proportions or means, you're looking for 0 when it's a confidence interval with two samples, okay? But when it's one sample, then it's not. Yes.
But we would have had evidence if 0 wasn't within the interval.
Yes, if 0 was not in the interval, you would have had evidence. Okay. All right. So that was the confidence interval. Let's talk about the hypothesis test. Okay. And I know it feels like terrible, like life is awful, but it's okay. Okay. If you were able to handle the hypothesis tests for a difference in proportions, you can handle a hypothesis test for a difference in means. Okay, it's the same concept. The only things that have changed is now you're using mu's instead of p's and x bars instead of p hats. And your standard error looks like this. And then you've got a degrees of freedom and t-table.
Wait, you're using news instead of
Instead of p's, okay? But the overall concept, this is, what I want you to see is, so I've taught statistics, so I can see everything at this high level, and I see this is the exact same concept, right? But when you guys are learning this stuff, it feels like, oh, I got formulas here, and I got formulas here, and everything's so different, okay? It's not. It's just, it's the same thing, right? It's like when you started driving, okay? Maybe when you first started driving and you got into one car, and it's the car that you learned on, and then you went to someone else's car, maybe you got flustered because the lights are now like, you have to pull on something, and then to go from park to shift, it's not down here, but it's you gotta go like this, and the parking brake's down the step or something, like it might be flustering to you, okay? But then at some point, like after you've driven for a few years, you're like, oh, I could drive any car because they're all exactly the same. It's just, sure, things look a little bit different. It's the exact same thing here, okay? It's just the same concept. It's just, it looks a little bit different because we're dealing with different things, but this overall concept exactly the same. It's just, sure, you know, when you're first starting out, it feels frustrating, right? And if you try to hit the brake and you hit the parking brake, you know, you're in trouble when you're driving. So if you do that kind of thing here, you're also in trouble. But we'll be okay. We'll be okay. All right. So here, the hypothesis test. Okay. The null hypothesis is always about mu, and it's going to be mu1 is equal to mu2. Always an equal sign shows up in the null hypothesis. Okay, or equivalently, we can write mu1 minus mu2 equals 0 also.
for hypothesis test. What do you
Hypothesis test for two samples and mean. Okay, this is hypothesis test for two samples and means. Okay, I should just say two sample means.
What's the title?
Huh?
What's the title?
I don't know, this is what the concept is right here. The alternative, okay, you have a choice. It could be not equal to, it could be greater than, it could be less than mu2, or equivalently, mu1 minus mu2 is not equal to 0, or greater than 0, or less than 0, right? And that decides if you multiply things by 2 or leave them as is. This is our standard error. We're still going to use this as our standard error. So our test statistic is going to be x1 bar minus x2 bar minus 0 over the standard error. And then we look this up in the t-table to get our p-value. And that's it. Okay? It's just, yes?
So we have X bar instead of where we usually have P hat.
Exactly. Exactly. Okay.
And for the standard error, we will use the same formula.
We will use this one. Okay? So let me, do I want to do this right now or not? Okay, so I'm going to try to show you how everything is exactly the same, but just a little different, okay? So all confidence intervals look like this. Okay. An estimate based on the data plus or minus a critical value times the standard error. All confidence intervals look like this. Okay? So let's talk about, we have confidence intervals for 4 different situations. No, I'm sorry, just 3 different situations. Okay? We have a confidence interval for one sample proportions. What is the estimate based on our data when we're dealing with a proportion and we've got one sample? Okay, so it's confidence interval for P. It's going to be P hat. This is our estimate based on our data. Plus or minus a z star, that's our critical value, times our standard error. What's our standard error? P hat times 1 minus p hat over n. But this is our standard error. Okay? Same form. This is the estimate plus or minus a critical value times the standard error. Okay. You already have all of this stuff in your notes, okay? So you can write this down. You can write this down. The important thing that I'm trying to get you to see is that is that they look alike, okay? So, I mean, sure, you can write all of this down in your notes, but you already have it in your notes. You should, okay? This is just going to be like a summary sheet if you copy it down, okay? But the important thing is that you see that they're alike. We made a confidence interval for one sample, but it was a mean, okay? So this was a confidence interval for what? Not X bar, mu, okay? What's the estimate based on the data? So if we're trying to estimate what mu is, what do we use from our data? X bar, plus or minus, and the critical value when we're dealing with means is now T star times the standard error, which is what? S over the square root of n. This is the standard error, this is the critical value, this is our estimate based on the data. Exact same form. Sure, the letters have all changed, but it's the same thing. It's just we're dealing with this. Okay, because it's a confidence interval for mu. Now we're going to make a confidence interval for two sample means. Okay, so this is a confidence interval for what? Mu1 minus mu2. Okay, what's my best guess for mu1 minus mu2? That's going to be my estimate based on the sample. No? So if I want to estimate what the difference between the means and the population are, my best guess right now is going to be the difference between the means of my samples, okay? So I'm going to do x1 bar minus x2 bar, okay? Plus or minus T star, and then the standard error is just this ugly thing.
Time standard error.
Right.
So all confidence intervals, they're of this form. What is the middle of this interval? No, the middle. Just what's the middle of this interval? Huh?
Understand the question.
What's the middle of the interval? What's the middle of the interval? What's the middle of anything? Well, what is it? No, not the mean. Okay.
The average?
No, it's p hat. P hat, right? P hat goes in the middle. If I take a sample and my sample shows 48% are going to vote for candidate A, I go 48% plus or minus whatever my margin of error is. Okay? That's my middle. What's the middle of this one? X bar, okay. And what's the middle of this one? X bar 1 minus X bar 2. Good. Okay. The margin of error is this entire thing, right? Critical value, these are, okay. Can we kind of see the parallels? Okay, so it's just like driving a different car where all the controls are in a different spot, but the overall concepts, you know, brake, gas, all of those things, all the same. Just they look a little different. Okay, don't get flustered.
So that's the critical value formula. The one we just wrote.
No critical value formula. Okay, critical value is either Z star or T star.
I meant
Confidence interval.
Yeah, that's right.
Confidence interval.
And the standard error stays the same whether you have 2 or 1. It's always the same for the mean, correct? Like the one that you gave us before is the same.
I'm not sure if I understand your question. I'm sorry.
For whether you have 1 sample or 2 samples, it's always the same formula as long as it's numeric.
No, the standard error for 1 sample proportion is this. The standard error for 1 sample mean is this.
Never mind.
Standard error
Okay,
for
yeah.
2 sample means is this. Okay, so I mean it changes each of these times.
It's not X bar 1 minus X bar 2 plus or minus T star times the square root of?
Yes, all of these are times. I mean, I didn't,
Yeah, they're all
I didn't put a
times.
little X there, but that's the times, okay? Alright. Okay. Do I wanna do this? Sure. Okay, so we got hypothesis tests. All hypothesis tests go like this. Okay. You have a null hypothesis and an alternative. The null always has an equal sign in it, and then the alternative will either have not equal, greater than, or less than, okay? If it's not equal to, then you double your ending thing, okay? The test statistic is always equal to basically your observed estimate from the data, okay, just like that, or estimate based on the data, observed estimate based on the data, minus whatever is stated in the null hypothesis, okay, the value in the null hypothesis, divided by the standard error. So all of our test statistics look like this. Minus the value in the null hypothesis in the H0. And then you look it up in the table and you find the p-value, okay? Look up test statistic in table, find the p-value. Okay, this might get tough.
The normal table.
In the T table.
Normal table or t-table, depending on whether you're dealing with what? Categorical or numeric data.
But with that one is
No. Okay? We're gonna have something, okay? Alright, so this is one sample proportion. Okay, is this categorical or numeric? Categorical, one sample proportion, okay? So, the null hypothesis will be P is equal to some number, okay, I'm gonna put in, I'm just making up a number, it's not always gonna be this, but P is equal to some number like this, and then the alternative is gonna be P whatever, greater than 0.4, okay? Alright? Then your test statistic is equal to P hat minus whatever number shows up in your null hypothesis, 0.4, divided by the standard error. What's the standard error?
Look at the t-table.
No, you go 0.4 times 1 minus 0.4 divided by n. Okay? And then now we'll look it up in the z table. Look up test statistic in z table. Okay.
This is categorical.
This is for categorical data when you're dealing with one sample. And this is just a very brief summary, okay? But it's overall to show this is the observed estimate from our data, right?
Yes.
The p hat is what we get from the data, just like that there. And what's the value in the null hypothesis? This is 0.4, okay? And then the standard error is this thing. There was a question.
I was gonna ask you where you get the from.
Okay? P hat comes from the data. How do we get that?
Says
Okay, so
-1.
if I interviewed 200 people
You can say n minus 1.
divided.
and I got 30 people said whatever, then I do 30 divided by 200. Okay.
Oh.
Okay. The other one is two sample proportions. We spent close to an hour at the beginning of class going over this. The null hypothesis is what? Okay, this is just one way to write it, but I'm going to put it in this way. P1 minus P2 equals 0, and then the alternative is that P1 minus P2, whatever, something other than 0, okay? The test statistic what is our observed, if this is what we're going for, okay, P1 and P2, if this is what we're going for in our null hypothesis, then what do we observe for? We just put hats over that thing. And so our observed estimate from the data is P1 hat minus P2 hat, right?
Yeah.
What value am I subtracting off that it shows up in the null hypothesis? 0, okay? Now, because it's minus 0, sometimes we ignore this, but this is in the, I just want to show that they're all in the same form here. And then what's my standard error? It's that ugly thing, right? P hat times 1 minus P hat times 1 over n1 plus 1 over n2, okay? And I just said, sorry, that's the standard error and there's nothing we can do about it, okay? And then just remember what P hat is, okay?
Don't we do first total success divided by total?
Yeah, to get P hat,
Yeah.
okay? But this is, I'm just trying to show how they're all parallel, okay? You got the null and alternative hypotheses, and then you got the test statistic, and then you look this up in the Z table, or you look it up in whatever table it is to get your p-value. Alright, again, sure, you can write all of this down in your notes. It probably already is in your notes. The key thing is, I'm just trying to get you guys to see how they're all parallel and the same idea. Okay?
Yeah, it is. Yeah.
Okay, well, it, you know, it feels that way, right? Well, okay, so I'm trying to show you, present the big picture to you, so you don't get lost in the details, but the details do matter, right? So you can be like, oh, I know brake and gas, but if you're using the wrong pedal when you're driving the truck, and rather than you're going to be in big trouble. So don't fool yourself into thinking everything is too easy, but it is overall easy. Okay, the details do matter, but the concepts are the same. Okay, so we got one sample. So we talked about proportions, and so now instead of proportions, we're dealing with means. So one sample mean. Okay, our null hypothesis and our alternative. The null hypothesis is about what? It's not P's, but mu, because it's about the population. Mu is equal to some number. I'm going to just make up a number. I'm going to say 30, okay? So of course not always going to be 30. And then the alternative maybe doesn't equal 30, okay? Whatever it might be. So then our test statistic is going to be equal to what?
30.
Not 30. What's my observed estimate from the data? No, I can't get mu. X bar, okay? What's the corresponding estimate that, what's the estimate that corresponds to what's in the null hypothesis? Okay, I do X bar, which is not mu, and I subtract off 30, the value in the null hypothesis, okay? I'm trying to get you guys to see that all of these things, we have an estimate coming from the data, in that case X bar. The number in the null hypothesis in this case was 30, and what's the standard error? So now we have to do S over the square root of n. Okay? And then we look this up in what table? Yeah. Okay, so then now we have degrees of freedom equals n minus 1. Look up test statistic in the T table.
Just to make sure.
Huh? Yes.
Just like, and when you're looking for the confident interval, that's when we use that one, right? For the one sample mean.
Yeah, one sample mean, that's the confidence interval, okay? So now, okay, last one, I know it's 10 o'clock, but just two minutes, we'll be out of here. Okay, we got two sample means. What is my null hypothesis?
Mu1
Mu1 minus mu2 equals 0, and the alternative whatever, mu1 minus mu2 greater than or less than or whatever, so I'm just going to do greater than 0, who cares, okay? Test statistic,
x1 minus x2.
x1 bar minus x2 bar,
Equal to 0.
minus 0, okay? This is the estimate coming from the data, minus 0, divided by the standard error, and what's the standard error? It's that ugly thing, okay? S1 squared over N1 plus S2 squared over N2. And again, you look this up in the t-table. Okay. So, the details do matter, okay? You can't just use the wrong standard error and hope to get away with it, okay? You've got to use the right standard error. You've got to use the right estimate of all of these things, okay? That is very important. But I just kind of want to show you that the overall concept for all of these things is the same. You've got something coming from the data, you're subtracting